exercise. Ну, точнее, proposition. We have a set of extensions. If we have a fixed G module M, then for a fixed G module we can consider a set of M extensions of G. And we have, in fact, a bijection between this set and the second cohomology of G in coefficients in M. How this bijection works? Second cohomology we can compute by bar resolution, and then second cohomology is classes of functions from G and G to M, maybe reduced functions. E, G, G1 is 0, such that they are cocycles. Cocycles means that we have something like this. For any triple elements GHK, cocycles. No modular differential of beta. Beta is any function from G to M, such that of unit is 0, also reduced. And dB is just function in two variables with the following definition. It's also cocycle, but it's coboundary. But okay, so what's the bijection? Yes, if we have an extension, we can choose some set theoretical section because it's surjection. Yes, it's pi, and it's I. Set theoretical section with the property, for example, this property. And then we can define cocycle depends on this section. GH is just, yes, in this order. It's element of E, but in fact, it lies in kernel of pi, yes? If I apply pi, I obtain GH minus 1, so it's unit. So in fact, it's in kernel of pi, and kernel of pi is M, so in fact, it's element of M. This is our function. Yes. Okay. Now let's check that this is a cocycle. First, check that this is a cocycle. It's a two cocycle. Maybe you can try. Check this on the board. No, yes. No, let's try to check this, but it's not very. No, it's.
It's very easy, I guess. Yes, what? So yes, an element of the group.
No, more or less obvious that it's reduced, yes, because if G and H or H are a unit, then it's of course 0. Yes, it's more or less obvious. Yes, we need to check cocycle condition. It's K, yes.
Yes. So this is by definition, I guess I'll check. Okay. Okay. Seems all right. Yes, now we need some simplifications. So we need to check that this is 0. So I guess we need to apply pi, because we know.
I think if you apply pi, you obtain 0 because it's in M. It lies in M.
No. Yes, pi is bad. Yes, pi is very bad. Pi is very bad. I want. Yes, maybe it's obvious from this setting. No. Yes, I want to use. I think I need to use that this is an injection. Isn't this? Since it is here, I want to take some preimage.
No, of course it's enough to check that this is unit in E. Yes, not in M. It's the same thing. First of all, do you know what does it mean? What is G dot on this? What does it mean?
This is some action that is somehow is.
Yes, but if we have extension, what's the action of G on M?
Let me try to remember.
If you have extension, what's the action of quotient on the kernel?
I think I need to take element G, take its preimage, yes, and then since I have a map M to E.
No. In fact, no. Yeah, no. Maybe yes, but this, in fact, this action does not depend on S.
Yes. So
okay, no, you can do this, and then.
Yeah, this is I, and if I take an element M, I need something like this. So M x on SG is so I need just two methods. I guess like this. Yes. In another direction.
No, you want to say that this is multiplication.
Yes. So G acts.
It can be multiplication because G I M does not lie in M, because if you apply pi here, you obtain unit and G. It's G. It's not unit. If you write down something like this, C S J I M,
yes,
and then apply pi, you obtain G, not unit.
Yes, this goes to 1 and this
to G.
goes to G, yes.
So it does not lie in M. It acts by conjugation. It acts by conjugation. If you have an extension, the quotient always acts by conjugation of the kernel. This does not depend on the choice of preimage.
So action is like this. G on M is.
No, and in fact, this, if you apply pi, this goes to unit. It lies in M itself. So this action is by, it's conjugation by G.
Yeah, so like this. Using S notation.
No, using S, but
because formally
this does not depend on S.
Yes. I mean, because formally this.
No, you can use S.
Does not lie in them.
You can use S if you want, but this action does not depend on the choice of
yes, okay,
of the preimage.
I understand.
Hello. We're doing an exercise. Oh, maybe you repeat the statement for our new guest.
The statement is like this. We have an extensions of groups. If you fix group G, yes, and we want to make a bijection between the extensions of G with abelian group M and the second cohomology.
M is G module. If you fix G module,
yes,
you can consider extension such that if you have any extension, you always have conjugation action of G on M, And you can consider such extensions where this action is the fixed action. You have fixed action on M. And you consider such extensions where you obtain some group here and you have the given action of G on M, okay? Such extensions. And then in fact this is in bijection with a second homology of G with coefficient in M, where we used bar resolution. If we use bar resolution, second homology class is just function into variables with values in M, such that with cocycle property. It's cocycle property. No, here was modular coboundaries. No, he cleared this. Okay. Now we we construct this bijection. We always can choose some section, set theoretical section, not group theoretical section. And then from this section, I can define this function. The first step, that this is cocycle. I want to define map from the left to the right. Now we want to check that this is cocycle. This is cocycle condition. Our first observation, what is this action? You can check that this element is from M, because if you apply pi, you obtain gh minus 1, it's unit. So it's in kernel of pi, it's in M. It takes values in M, in fact, in kernel of pi. And on kernel of pi, we have action of G. In fact, this is conjugation. It's conjugation. This conjugation action does not depend on the doesn't depend on choice of preimage of G. G acts on M by conjugation by any preimage. For example, S of G, but it's not important. Okay, so here, in fact, we have kind of preimage, yes.
So now we can.
For example, S, but in fact, it's not important, yes. Conjugation by any preimage is the same. I think it will be important for the.
Minus.
No, yes. You can, we know that this is a abelian group. You can interchange some terms. And then, in fact, you can then write down them multiplicatively in E. Because, in fact, here, minus and plus, it's the same operation as multiplication in E. No, if you want, you can apply I and do this. I think it's a good thing to consider this thing plus this thing and minus this thing and this thing. And do this, if you want, and do this multiplicatively in E. Then you have some cancellations.
What do you mean by E? This is an element in E, since it is S of something.
No, in fact, this is elements in M. Yes, this is element in M.
I mean,
what you want? This element is M. Yes, you're right. Do you agree? By definition, what we doing?
Yes, this is from identification.
Yes. It's by definition. Yes,
this is if you want. This is preimage.
What I want to say that you can interchange these two terms. Consider sum of this term and this term, and this term and this term. And if you write down these sums in multiplicative notation in E, not in M, because then you have some cancellation. This cancellation in E, not in M, because some elements will not lie in M.
Okay, let's see.
Okay, yes, consider sum plus a third element. For example. And then minus second and fourth.
Yes, minus.
Mhm. Or maybe, no, maybe, in fact, it's more convenient this first and then this.
First and
Oh,
last?
yes, this first. This first. And then this. Oh, maybe I don't know.
Right. Okay.
No, because now if you consider these operations as operations in E, you have some cancellations here, yes? It's multiplication. It's just this plus and minus is just multiplications in E. Okay? No, our operation in M is induced by operation of E. It's just subgroup. M is subgroup in E. Okay?
Yes.
So in fact, this plus and minus you can
okay,
yes.
I see. This
You can interpret them yes as a multiplication in E, and here you also have cancellation. Yes.
Okay. Yes, you're right.
What else? Well, here you have another cancellation.
Yes.
Okay. So what we obtain? Finally, we want to obtain unit. No. Okay. I think it's makes sense. Just write down it as one word in multiplicative notation, in notation, maybe.
Okay. Yeah. Okay.
It's -1 then. Yes. Because
yes,
it's -1.
Yes, you're right.
And then. Yes, it's inverse of this word. Yes.
And then it's also cancels. No. GHK.
Here it's also because it's from this.
Yeah. Okay. So no -1 here.
Maybe because they will not cancellate in else. No, it's our claim. We don't know this. Yes.
Yes, we want to prove this. You're right.
It's all you. Where is -1 here? Here.
Here. You're right.
Why it's K? What?
It's H in your. Is it H?
Here. What is this letter says H? Yes,
This
if
is
it's H. What is
Okay,
H?
so this is H here, and this is -1.
-1. No, SK also -1, I think.
Yes.
So
like this, yes.
Or
Also right.
no, we have cancellation. Yes. Now we see that we have cancellation.
Yes, this is here.
Or. Okay.
Yes. Wait a second. Yeah, so without identification, we take. I think we take a pre-image of this without identification.
No, maybe. No.
Yes, because when this is.
No, in fact, I think it's more convenient to think that I is just inclusion of subgroup of E. This subgroup is abelian, so sometimes we can use additive notation in M itself, but it's just abelian subgroup of E. Okay, no, I think it's not make large sense. No, remember these identifications because it's just two subgroup.
Okay, but I once said that it's hard for me to. I use very formally.
No, okay, then it's monomorphism from abelian group to E. Yes. Here we use I -1, and then we apply I if you want. Okay.
Yes.
This is my. Okay. This is cocycle. Okay. It's a reduced cocycle because if we here GOH is 1, then it's unit 0. Okay. Oppositely, if we have a cocycle, then we can obtain any cocycle from some extension by this procedure. If you consider any cocycle, to cocycle, then there exist extensions and sections such that the corresponding cocycle is this cocycle. It's this construction E phi is just Mg as a set with the following operation. The following operation. Do you agree that this is a group with this operation? No, maybe you need to check this. Associativity maybe needs cocycle condition. No, we have unit. Unit, it's obvious. Unit is 0, 1. It's because this reduced cocycle. It's also important here that if it's 1, that it will be 0. Okay. Now let's check. Okay, you can check that this is associative multiplication using cocycle condition. So we have monoid. Yes. Why we have inverses? In fact, to check inverses, I want to define section. Okay, we have this. I can include M as M0, M unit. M unit is the subgroup of this group. If we believe that this is a group, then this thing is a subgroup. Isomorphic to M is inclusion. And on the other side, we have projection to G, to the second coordinate, and kernel is exactly this subgroup M. So we have an extension. And in fact, we have more or less natural section here. Just 0G. It's not group action. It's not group section because multiplication of 0G and 0G prime is phi G prime G prime. If phi is not 0, then it's not group homomorphism. If phi is 0, as I said before, it corresponds to semi-direct product, and this is exactly extension which has group section from the right. Do you understand what I'm saying? Multiplication of such two elements, it's GG prime, and this is cocycle on the left, yes? So this section is group section if and only if phi is 0. Okay. This is section. So we need to check that phi s is phi. To do this, by definition, phi s of GH, it's S G S H GH minus 1. Okay, it's simple, but we need to understand what the inverse element, at least for such elements. What the inverse in this group? You can do this directly by definition. Again, if we believe that this is group, then you need to solve the equation that if you have given element, you need to find another element such that this thing is 0, 1. So the second coordinate, of course, it's the inverse in the group G, and you need to solve this equation no, it's solved because it's linear, yes? So mg inverse is, no, I have this equation, it's 0. And I know m and g. So m prime is minus m minus phi g minus 1. Minus m plus phi g and g inverse, because here, no, g prime must be g inverse. We know this. And then g inverse from the left, g inverse, something like this. No, it's by definition, it's left inverse here, yes? Oh, sorry, it's right inverse. No, you need to check that it's also a left inverse, and this is a group structure. So this by definition left, right inverse. No, you need to check that this is a group, so this is also left inverse. So it is really inverse in our group. Okay. Mm-hmm. So oh, maybe okay. No, if we have here, we have 0g, 0h, and inverse of 0gh. If m is 0, then this is 0. We have such thing. So this is minus gh minus 1 phi of gh minus 1 gh minus 1. And we need to multiply them. Multiply in this group. Now, if I multiply these elements, it will be phi gh gh. No, of course, on the second coordinate we obtain unit. We obtain unit. Okay. What we obtain? No, I want to check that on the first coordinate I obtain exactly this thing. Exactly this thing. Okay. On the first coordinate, I obtain phi gh. It's okay. Plus gh action on this. And plus phi gh minus 1. No, okay. And we see that this can cancellate elements, yes? We have, this is elements, this is minus phi gh minus 1, and this is phi gh minus 1, okay? Yes? So we obtain really phi. So phi s gh equal to phi gh unit. No, by definition, it's our phi gh is as if we identify these elements with m. It's our cocycle. Do you agree? Yes. Okay. Now, what happens if we change a section? If we change a section, consider another section, S prime. No, because this is two sections, there are two elements, there are two functions with values in group E. No, of course, any two functions with values in some group, they differ by some functions with these values in this group. Do you agree? No, I can just define this by this equation, okay? This is definition of beta. just difference between them. Okay, because of the takes sense unit to unit there, so beta is also sense unit to unit. Unit to unit. P is G to, yes, and G and beta takes values in M, because if I apply pi, I obtain unit, unit, and so beta is also unit. So beta sends elements to M. Oh, okay, if I apply pi to G, pi I obtain G, pi beta G, G. So pi beta G is unit, okay?
Yes.
So it's in fact, by identification, it takes values in M. It's our one cocycle. We want to check that, no, it's not one cocycle, it's one chain. We want to check that codifferential of this cochain is just difference between our two cocycles. It's our candidate. No, okay. Let's check something like this. Let's compute something like phi s prime minus phi s. I use multiplicative notation in E. No, and use this thing. Yes. So this is beta G S G, beta H S H, beta GH minus 1. Sorry. Okay. Сейчас, тут есть несколько выборов. Давайте я посмотрю, как это правильно сделать. Yes. GH minus 1, beta GH minus 1, SGH, SH minus 1, SG minus 1. Ну, окей, давайте я напишу, как я писал у себя. Сейчас я решил немножко по-другому. Давайте сделаем, как там у меня было. Let's define like this, okay? Beta. Okay? Now then we obtain here something. G beta G, SH beta H, S beta GH minus 1, S GH minus 1, S GH, S H minus 1, S G minus 1. We have cancellation, and what is it? What we obtain? Yes. What this thing is conjugation by S of G. Is G action in our M module. So it equals to G action in our M module of what? Of BG, beta G, plus this is action by H. So it's H action plus A action of what? Of BH, beta H. Plus minus BGH, beta GH. What we have such, no, this is equality. This is the same thing. Okay? I rewrite this in terms of G action on M and addition in M. Okay? Do you agree? This is external conjugations, external G action. This is BG plus this is H action on this. This is BH minus BGH. No, and this is, it's not just coboundary of beta. It's not exactly coboundary, because coboundary of something, let me recall, coboundary of one chain, coboundary of one chain is this thing. But, no, okay, if we define beta tilde by G action of beta, B tilde, it's G of B, of beta, then this thing will be equal to GH beta minus GH of H, yes, GH. Oh, stop 1 second. Sorry, I have another, sorry, yes, plus B tilde G. It was incorrect in the very first row also, it's 3 terms. So I have where last term disappears, it always exists. Plus G beta G. No, and then I think it's the same, it's exactly this thing, yes, GH, B, GH, GH what? So this is coboundary of D B tilde. Modulo this twist, no, this also cochain, also cochain. Maybe it's not very good that this cochain is not reduced. This cochain is not reduced. No, sorry, it's reduced. It's reduced cochain, because if I have unit, then it's 0, and no, action on 0 is 0 on M. Yes, it's reduced cochain. It's reduced cochain such that its differential, codifferential is our difference, okay? No, something like this. So what we obtain? We obtain that we construct correct map from extension to cohomology, because for any extension I choose some section, obtain cocycle. If I choose another section, I obtain cocycle differs by coboundary. So it's correct map to cohomology classes. Cocycles modulo coboundaries. And this map is surjective, because for any cocycle I can construct extension, as I said before. So it's surjection. Now we only need to check that this injection. No, injection, why it's injection? If I have 2 cohomology classes equal, if I have 2 extensions and I obtain the equal cohomology classes, no, what does it mean? This means that I have 2 sections, two extensions. I choose 2 sections and obtain the same cohomology classes. This is SS, this is S prime. No, I always, by this construction, if I consider, no, this means that the difference between phi and phi S prime is differential of some B tilde. No, if I consider this B tilde and define beta by this equality, another function, then by this calculation in the inverse direction, I obtain that for this beta, I have that sections differs exactly by this beta. Exactly by this beta. So this means that sections differs by this beta. And so, no, this means that I can. No, this means that I can redefine. So this argument says that I can redefine one of the sections by this beta, such that no, the sections will be coincide. I can consider another section, S, and S2 prime, S prime beta. And this is also a section. This is also a section for another extension, and these sections just coincide. So sorry. This means if I redefine this section, then these cocycles will coincide. Yes, this will be 0. I can twist one section by this beta, such that cocycles just coincide. So if they differ by coboundary, I can twist section to obtain this difference coboundary will be 0 just by this calculation. It's exactly the same trick. Okay?
Can I ask a question?
Huh?
I think I didn't notice this moment, but when we consider, so if you want to prove that this is inverse, so we need to take the two arbitrary homological classes.
Yeah, two extensions. We have two extensions.
So what are you trying to do?
No, I want to check that if I have two extensions, I choose some sections, obtain some two homology classes. I want to check that if these homology classes are the same homology class and is in homology group, then extensions are isomorphic.
Yes. But the question is, so you take two homology classes. Yes. The question is why we can always take the representative of the homology classes phi S or something.
No. My homology classes by definition is I have two extensions and I have images. This map works in this manner. No, in fact, we know that this is surjection. We prove that any homology class can be obtained from some section for any extension of extension if you want. But it's not important here because here I have I want to check in English. I have two extensions and consider the corresponding homology class. It construct by some sections.
Yes, you're right.
Yes. So and if they differ by beta tilde, I can twist one of these sections, change the section such that they just coincide. So I can, in fact, because I know that. Okay. Yes. Okay. So I just proved that I can choose another section of one of my extensions such that cocycles just the same cocycles. So I need to check that if I have two extensions and two sections such that cocycles coincide, then extensions are isomorphic. No, it's exactly more or less the same construction. The same construction. We have bijection. But for example, for one extension, I have bijection with mg, which sends e to pi e, and e s minus 1 pi e. Yes, something like this. It's bijection, more or less because it's extension. It's bijection of sets, and yes, and what if you want to obtain, and you want to define group structure from this bijection, induce group structure. And if you write down definition of this induced group structure, you obtain that this group structure only depends on cocycle. Only depends on on cocycle. On cocycle, yes, because we have S here. This group structure depends on cocycle.
Is it S minus 1?
No, yes. No, because just you apply pi and obtain E. To lie this in M.
No, I don't understand.
No, I want this element to lie in M, in kernel of pi. If you apply pi, you obtain pi E and pi E minus 1.
No, I mean, just by diagram, I don't understand how we can apply this. I mean, pi of E is in G, but I cannot use this minus 1 from G.
Pi is group homomorphism.
Yes.
It sends S minus 1 to inverse, to pi E, pi S minus 1 pi E. It's equal to pi S pi E minus 1. And this is identity, this is pi E minus 1. What if I apply this G? Pi is group homomorphism. It's inverse element of SG. So this is, you apply pi to SG and this then inverse. And this is G. Because, so this is G inverse.
No, I don't understand. You're taking composition of function, composition of S minus 1 and pi. But
Yes.
composition is not defined.
Why?
Try to draw a conjugative diagram.
Ah, no, it's not inverse function. It's inverse of element. S of pi, I know, of course, because it makes sense. It must make sense. It's just inverse of element. No, it's kind of projection. You have projection, then some inverse, and I have orthogonal part. The difference between x and projection. Okay. And then it goes to unit by pi, so it's lies in M. No, it's kind of the first the M coordinate of any element. It's difference between projection and then section. It's always the first coordinate. No, and you can check that if you induce group structure from this to this, then this group structure depends only on Fs, phi s. So if you have two cocycles, then you have two group structures, and they coincide. No, so this is group isomorphism, and so you obtain group isomorphism. Identity on M and G, so it is isomorphism of extensions. Okay. No, you need to check this. That group structure depends only on F phi s. Oh yes. Okay. A little bit another. Okay. Yes. Now let's say about. Так, сколько времени там? Сейчас я подумаю, про что сказать. Ну, про Линдона, наверное, надо говорить. Так, okay, this is the end. So far. About this bijection. Yes, and zero homology class corresponds to semi-direct product. It's extension when you have a right inverse, group inverse. Okay.
All the extensions are direct products, they are isomorphic. Semi-direct.
Semi-direct product. Yes, it's when you have group inverse here, then E is M G. Yes. No, you also have G action here. If this semi-direct product is direct product, if and only if this G action is trivial.
But the action is fixed.
G action is fixed. Yes. You have fixed G action, and then semi-direct is when you have inverse, right inverse, and it corresponds to zero homology class. Yes, because to say about homology, you have fixed coefficients. Yes, fixed G action.
Then
Yes, 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 yes. The last time we have for any ring homomorphism, I again recall base change spectral sequence. For any ring homomorphism, I have spectral sequences. This one, так, сейчас я вспомню. S, N, is over R over S. Here N is R module, M is S module. This is also S module from the left multiplication by S. And it converges to P plus Q over S to M to from N to N. And for homology, for Tor, the same thing. No, it's yes, it's classical things. We discussed it in the beginning of the course. It's just spectral sequence of cochain of B complex. You need to consider some projective resolution of M, and here injective resolution of N. Then consider home B complex, and from this home B complex you obtain this spectral sequence. And here you have projective resolution of M, projective resolution of N, and then consider the tensor product. You consider something like this P. Then it's R projective resolution. It's S projective resolution of M. Then over R S R Q. Q is R projective resolution of N here. It's B complex, and two spectral sequences of this B complex. One spectral, as always, one spectral sequence gives you second page, and another spectral sequence gives you the target. And here the same thing for home. From projective resolution to home from S to an injective resolution. Here B complex over R. It's injective resolution of R module N. This is projective resolution of S module M. And this is B complex, and again, two spectral sequences give you this spectral sequence. Okay, in our situation, if we have short sequence of groups, then we have, for example, we have, okay, let me recall what I want to say. We have, consider at first this, we have group rings, and we have this group rings homomorphism. For this homomorphism, I apply the, for example, the first spectral sequence. What I obtain. This is R, this is S. So I have over Q, right? Yes. M will be equal to Z, and N will be equal to some G module M. Converge to this thing over S. Okay. This is to M. Sorry, because here, of course, here R. No, it does not make sense because one of this module only R module. Yes, and here R. Yes. G. because M is G module, it's not Q module. Whoa, we have this spectral sequence. No, this is just cohomology of G in coefficients in M. What's this? No, this is cohomology of Q in this module. What is this thing? No, here we also can use another spectral sequence, but in fact, here it's easy one thing, because in fact, no, what I have here, M is left G module. I consider the Q as right G module. No, this is right G module by this homomorphism. But I claim that this right G module is free module. No, sorry. Okay, let me consider ZQ. It's right G module. Okay, as G module, of course, it's not free. But I can consider this another group homomorphism, ZH to ZG. This is a right ZG module. Сейчас я просто хочу это как-нибудь попроще сказать на самом деле. Вот, let's try to compute this X. Consider this thing. Consider resolution of Z over H. It's projective resolution over ZH. No, as ZG. Вот так, ZG. Consider this projective resolution. And then consider tensor product of this thing. Or maybe of M. Yes. Consider projective resolution of G module M, and consider tensor with Z over H, because M is also H module, because we have this ring homomorphism. M is left G module, is also left H module, and I can consider tensor product with right H module Z over ZH. Okay. What I have this. So what I obtain P Z over ZH tensor P dot. This chain complex compute. It's homology. I need cohomology. I need hom. Oh, it's not important. Hom from Z over H. Hom from Z to P dot over H. This chain complex compute compute what it compute X from Z to M over H. So it compute homology of H in coefficients in M. Okay, but here I want to obtain the following observation: ZG as left H module is free. Oh, it's free left H module. It's free left H module. Because it's direct sum of ZH over Q over cosets. Yes? Any element of G lies in the unique coset. You can choose some representative of this coset and obtain the basis over H. So, and okay, I can here consider free resolution. Free resolution. So this is free G module, so this is free H modules. So what I obtain? It's extended module over H. What I then obtain? No, then this thing is just invariance invariance of this free module, what is Hom then from Z to ZG? No, invariance of this thing, I want to say that this is just ZQ, just ZQ. ZG is isomorphic to ZQ. And coinvariance also, because it's free module. In fact, maybe it's not really true if Q is infinite. If Q is infinite, this will be direct product, not direct sum of elements of Q. No, then I think it will be some issues with spectral sequence also. Cohomology. No, sorry, it's not. No, not sorry. Okay, sorry. Yes, it's not true. Yes, it's just Hom. Well, because it's free module, I can cancel H. Yes, so it's Hom over Z from Z to ZQ. Oh, this is true. Sorry. Okay, because it's free module. Hom to free module, you can cancel your ring structure to abelian groups. No, this is true. This is true? I think yes. Oh. And so this cochain complex compute you compute cohomology of H with coefficients in M, and this is the same as X from Z to ZQ. No, ZQ M, what I have here. It's not the same thing. Okay, sorry, it's maybe, I want, сейчас, что тут хочу вообще? Okay, I want that this thing is isomorphic to cohomology of H in coefficient in M. This cohomology computes this thing, and I want X from ZQ to M. From ZQ to M. Да, вообще не то. Все не то. Сейчас. Потому что I want homology from ZQ to M. I need either injective resolution of M, or I need projective resolution of ZQ. Then yes, M. Maybe something like this. Oh, yes, and then I consider just standard product over H. What? And here I just want to apply this observation. This is free module, and then this standard product is left. I think is isomorphic to ZQ. What? This is more or less obvious from this description. Yes. Okay. It's coinvariance. And this is also yes, and this is and this is also right Q module. This is a right Q module. It's right Q module. Okay, it's okay. So if I apply this, I obtain free ZQ. No, chain complex of free ZQ modules. What I obtain? It's free ZQ modules Why we do this? Why I do this? Так, нет, что-то я делаю не так. Что-то я делаю не то. Или нет, то. Just 1 second. I just consider my free resolution starts with ZG and then other free terms. And then I apply tensor with Z over H. I obtain this is exactly ZQ, and then some free ZQ modules. They are free because it's they have because it was free ZG model. If you consider H, it will be it was direct sum of ZG, so it's direct sum of ZQ. Okay, so this is some chain complex of free ZQ modules, and I want to say that this is Нет, что-то я тут делаю не то. Так. Или все нормально? I want to check that, then I need that this is resolution. It's free, maybe it's free ZG.
Почему тут R? Если мы так считаем.
Не, пока я ни при чем. I think I want free G resolution of ZQ. What I want to check? I think this. I need this. I need free ZG resolution of ZQ. As right R module, as right G modules. As right G modules, it's free resolution of ZQ. What is free resolution of ZQ as right G modules? It's okay. It's bar resolution, for example. Okay, yes, sorry. Yes, again. Consider, yes, it's true. Consider, just 1 second. Have Z, G, M, H. Okay, consider bar resolution. Bar resolution for Z. It's a bar resolution over G. And if I yes, and now I want to apply this resolution to M over H. Then this gives me this homology. What on the other side? I have that. Yes, I have that. This free module over ZG. Yes, I want just say that this is Hom over A over G from resolution for ZQ to M. Окей, ладно, я сдаюсь, надо специально последовательно написать. So we have another spectral sequence, third one, third base change spectral sequence. of the form between Tor and Ext. I have a spectral sequence of this form, Ext P S Tor Q S M R and converge to Ext. Okay, it's always true. And then in our situation, we have for this inclusion, we have spectral sequence from it's G, this is H, this is H. M will be Z. This will be M, Z, and S is Z, ZG. Yes, and here this Tor is always it's almost always 0 because ZG is free H module, as I said before. ZG is free the H module over Q. No, it's kind of the H, the Q, something like this, over Z. As left, H module is this thing, and as a right. No, it has no right Q module structure. Okay, then it's free the H module. Okay. Yes, and no, so all this Tor are 0 except of 0, 1, where tensor product with Z is just ZQ. Z, H, ZG is ZQ. So we obtain that we have only one row in the spectral sequence, and so this thing, in fact, is isomorphic to Ext over G from ZQ to M. Well, okay. So the thing is, in fact, yes, we have this isomorphism. Okay? I have spectral sequence, and all these parts are 0. So in my second page, I have only 0 row. And if I have 0 row, there, so in each diagonal only have only one. No, if in your spectral sequence you have only one row, then infinity page is isomorphic to elements of this row. In each diagonal, I have only one element. So my target is isomorphic to this row. Mm-hmm. Because ZG is free ZH module. And the tensor is 0 Tor, its tensor product is just ZQ. So this, okay. So we obtain Lyndon, Hochschild, Serre spectral sequence, homological spectral sequence. HQ, HM, homology of Q is converge to GM. If M is trivial, then it's Serre spectral sequence for the corresponding Serre fibration of classifying space, but it's only if M is trivial. Okay. And you also have the for homology, the same thing. What for homology, I in fact want more direct description in that second. Okay, and for homology, the same thing. Okay, now if you have a spectral sequence of the first quadrant, you always have 5-term exact sequence. Now, for example, consider homological one, because I want to consider homological one first. If you have spectral sequence of homological type, for example, homological type, I have this differential. So I have, this is 2, 0. 2, 0, it's my homology of Q. 0 homology of, or second homology of Q. Yes, and I want now consider this spectral sequence for M is Z. It's just Z. No, in fact, it's not very, no, okay, maybe okay, for M. For M, we have, in general situation, we have Q in M is 0 homology, it's coinvariance, MH. Then I have, it's this element. Have differential to this element. It's first, it's 0 homology of Q in first homology. So it's coinvariance of first homology of HM under Q. And now argument with filtrations. Yes, we have this filtration. I have homology of G. It has filtration. It's degrees in filtration. So it's F1, F0, F0. It's and quotients are, yes, it will be. I hope it will be something like this. But this is quotient. Huh? I want to check that if I have spectral sequence of the first quadrant, I want to obtain some some 5 terms exact sequence. In general, what if I have spectral sequence of the first quadrant? I have these elements. I have differentials. It's my differential. No, in my particular case, but it works always. Okay, I have differential. Now, in this diagonal, the first diagonal, I have filtration on my target. On my it's first diagonal. Okay, on first diagonal, on the first grading of my target, I have filtration to filtration because it's spectral sequence of the first quadrant. Quotients of filtration is my infinity page. So I have this quotient and this quotient. So I have extension. It's always for this thing, for my target. Okay. But what is in this place? It's 0, 1. Infinity page. No, yes, infinity page is exactly the co-kernel of this differential because I have only one inward differential and no one outward. Yes. So infinity. What this thing is just co-kernel of this differential. Okay. Do you agree? At this place, the only non-trivial differential is this differential. If I consider co-kernel, I obtain third page, and this is exactly infinity page already. Okay, at this place. No, and here is kernel of differential. So, in fact, I have here I have kernel, and I have kernel, and I have projection on kernel, so I can write here H1 of my target. And this will be exact in this place. And always here I have co-kernel, and this co-kernel also includes two. Yes, because here, no, sorry. It's co-kernel. No, but this is not true. Sorry. What E1 infinity, it's this infinity, is just E1, 2. Because here I have no one non-trivial difference. Yes. So here it's just E1, 2. It's my kernel. So here I have E1, 2. It's just, what is it? It's my. No, sorry. Yes. Okay. Let's. Okay. Here I have co-kernel. Co-kernel is this thing, and this is H1. H1 GM. Okay. What's here? Kernel of Yes, and maybe, and yes, and the quotient of this map is exactly E1, 0, 2. This is first homology in coefficients in coinvariance. First homology of Q in coinvariance. The second is the first. What? And this is surjection. So this is almost the end. It's 4 terms, and I have another term here. What the kernel differential? Kernel of differential is exactly E infinity page. Kernel of D2 it's infinity page of 2, 0. And in H2 I have filtrations F2, F1, F0, and this is quotient is exactly infinity to 0. So I have surjection from H2 to this quotient. So I have kernel here, it's this quotient, and I have surjection from H2. Well, I obtain 5-term long existence. It's not exact on the leftist time, it's exact in these 4 places. Okay? It was an exercise of Serre that if you have some kernel of zeros, then you can obtain some long. Serre long existence. Not infinite, but finite, but longer than this. This works for any first quadrant spectral sequence. Okay? Do you agree? Okay, so we obtain this first 5-term existence. Just for a second, we also have the corresponding thing for cohomology. For cohomology, the dual things works. I hope it works on the same thing. Maybe, no, I hope yes. No. It's homology. It's on the opposite direction. For homology, we have 0 first homology Q MH. Yes, 2 first homology. No, the same thing, the opposite direction. And this is, I want just notice for a second that what if I consider extension again, I can give you more functorial and more conceptual description of the bijection between second homology and extensions. If I have extension, then I can consider this extension as the sequence of groups, and so I have such long exact sequence where Q is G.
What is this MPG is extension of?
What? No, extension of. I consider my extension by a abelian group.
So you fix them.
No, as always, I consider some molecule, I consider extension, as we considered previously. This is a sequence of groups, short sequence of groups, okay? So I have a long sequence of homology. I consider this one. This one, it's just differential. It's differential. Second differential of my spectral sequence. And M here is Z, it's trivial module Z. So here, here H is subgroup with M. So it's from homology of M in coefficients in Z. Invariance under G, yes. Goes to second cohomology of G coefficients in Z. What is this? Now we know that. What is this? We know that what the first homology. Oh, sorry. No, yes, sorry. Yes. Now M is abelian group. What the first homology? We know what the first homology. First homology is home. First homology is at home from the first homology to Z. First homology is abelianization, but M is already abelian, so it's just home from M to Z over Z. And G action. What the G action here? No, G action here is just by action on M. No, maybe it's important for a second, it will be also important. If you have two G modules, you can consider home over Z from M to N. And this is also a G module. You can consider G action on F, on M is something like G F J minus 1 of M. By conjugation. It's left action on home, and invariance under this action is exactly G invariant maps. Yes, it's maps of G modules. Invariance of this module. I want to consider this at a second. I want to consider this after Hopf theorem. But no, yes, this is home over G. And here this is action. Here Z is trivial and this M. So this is just home of G models from M to Z. From M to Z. What is this? What does it mean? Sorry. Why? No. Sorry. I won't consider not trivial Z. I want to consider coefficients in M also M. It's as G module. Yes. Sorry. I consider the situation where I consider M as a abelian group and also as a G module. Here I consider this as G module. No, then it's also true. That's G from M to M. So we obtain map differential goes from home from M to M to second homology. No, and the corresponding class is the image of identity. Identity goes to class corresponding to this extension. Okay, so this is a functorial description of this corresponding. You can consider identity, and then image under differential is exactly the cocycle corresponding to extension. Okay, in this situation. Okay, now about homologies. Consider now I want to consider trivial module M is Z. What we obtain? Now this is coinvariance of Z is Z. First homology, second homology. No, okay. No, this is just abelianization. It's for any group homomorphism we obtain induced homomorphism on abelianization. So it's okay. The abelianization to abelianization. Now we only need to check what this thing, what the Q action on the abelianization of H. We have some Q action on abelianization of H, and what is it? Now let's check this. No, I claim that this is by conjugation. If you have some kernel of some quotient, then Q acts on abelianization of H by conjugation. And this is exactly a coinvariance of this action. But we need to check this.
What are we trying to prove
now?
What are we trying to prove?
I want to understand what the Q action on this abelianization. To understand what's the coinvariance, I want to understand what the action.
And why do we need this?
Because I want to understand what's coinvariance.
Okay, so we don't have any general goal to prove something.
General goal to understand something. Okay? General goal, no. for any extension, you have this you have this exact sequence. I want to understand terms, okay? Because it always exists. These terms I don't understand because I don't understand second homology. But here I understand first homology. It's just abilization. But no, what's the action? What the general universal action of quotient on abilization of H? That always exists. What is it? I claim this is by a junction. Again, something like this. So you consider some coset Q. You consider any pre-image and then conjugate this thing. And this thing it's from abilization. It's also does not depend on the choice of pre-image if you consider this as the element of abilization. And I claim that it is this action. Okay, let's check this. Let's check this. Так. What, and here I want to consider what I tried to consider before, some resolutions. I want to explicitly understand this thing. It's the first homology of H in coefficient Z. Why it's Q module in general? Because I know that it's isomorphic to Tor 1 over G from ZQ to Z. Yes. And this thing has a left Q action. So I need to understand this identification directly to understand Q action on this. Okay. In general, we obtain this from spectral sequence, and now I want to understand it directly. So because here, more or less obvious Q action. Consider Q resolution, and then you have Q action on this thing. Consider G resolution of Z, then tensor with the Q, and you have Q module structure on this tensor product of G resolution of Z and ZQ. So on homology, you also have left ZQ structure. So I need to understand this identification. Why this is true in general? But again, I consider G resolution of Z. G resolution of Z. Вот это у меня написано, это должно сойтись. Значит, maybe even, for example, bar resolution, or for example, bar resolution, free resolution, it's not very important that it's bar resolution, maybe bar resolution of Z over G. Then apply tensor with H, with Z over H. As I said before, ZG tensor with Z over H is ZQ. So if I forget this part, as always, I obtain the following chain complex: ZQ, ZQ, ZG, ZQ, ZG squared, and so on. Chain complex. This chain complex exactly compute this thing. Okay, I consider G resolution of Z and then tensor with the. It computes this thing. I consider G. No. It compute nothing. Okay, sorry. It compute. It compute this thing. Yes, this compute this thing. No, because in general, yes, if you have its resolution, its exact sequence of G modules, but each ZG is also free ZH module, as I said before. Yes, ZG is free ZH module, so it's also free ZH module because it's sums of ZG, and each ZG is free ZH module. So it's also H resolution. Yes, G resolution is always H resolution. Okay, so each H. I consider G resolution, but it's always. This is the main observation. I can consider G resolution, but it's also H resolution of Z. Okay, because its resolution is exact. And if I consider it as left H modules, they also free because ZG is free H module. Okay. And this is direct sum of ZGs. Each ZG is free ZH modulus, direct sum of some ZH, okay? So this is in fact also H resolution. And then if I consider this thing, I just compute this homologies, okay? Do you agree? No, the only observation is that free ZG resolution of something is free ZH resolution of the same thing. Considered as H model under radical model. Okay, so this chain complex, in fact, compute this thing. No, and okay, and from general spectral circuits, for example, we know that these homologies are isomorphic to this thing. But okay, in fact, maybe I don't need this identification. But from this thing, I obtain, I have left Q model structure already, okay? I know that this complex compute me homologies of H in coefficient Z. And my Q model structure is from Q model structure of this complex. It's my claim. So it's homologies of this sort. And I have Q model structure here. Because this chain complex has Q model structure and all differentials are ZQ modules. ZQ model structure, okay? Do you agree? Okay, so in fact, I obtained that ZQ model structure on homologies comes from ZQ model structure on this chain complex, which homologies is this homologies. By this observation, that I can consider not just H resolution, but G resolution. And then, if I tensor it with Z over H, I obtain, in fact, a chain complex of ZQ modules. So I obtain ZQ model structure on homologies, and so I want to understand what the model structure on the first homologies. First homologies is just, it's this kernel of this map modulo this map. So these maps is just resolution maps, bar resolution maps. I know them. What these maps? Yes, here maybe I need exactly bar resolution because in bar resolution I know all differentials explicitly. So the first map, kernel of what I want to consider. It's the following map. Yes. Maybe I consider Q tensor G. It goes just to QG. Q is some cosat quotient class, some minus Q, of course. Yeah, by bar is what? It's just bar differential. I can consider any quotient class. I can multiply them by G, by element of your group, because it's quotient class. And consider this difference. Okay, it's bar resolution. It's bar differential. Okay, do you agree?
Is it from where to where?
No, from this. It's map in bar resolution, just something like this. Okay. And I have here I also have some map. Okay. Now what the action? So okay, let me. I will return to this. What the action on first homologies? So for example, what the representative of the homologies here? In fact, it's abilization. Yes, it's abilization. Any element of this abilization represents by some element of H. What the element of this chain complex represents the same class of H. In fact, it's just elements 1H. 1 is coset of unit. It's coset of H itself. These elements, it lies in ZQ, ZH. It's cocycle because by this map, where it goes 1H, but 1H is the same coset as coset of 1 because we consider cosets modulo H. And this will be H minus H, so it's 0. So it's cycle. It's one cycle, and in fact, this one cycle corresponds to elements of H here. So I have left action. I have left action by definition something like this. Obtain this This is my left action. I need to rewrite this thing in this form, 1 on something. So and then I obtain what this action means in the terms of h itself. Okay. No, here it's just calculation in bar resolution. What here I need this map because I need in homology modulo some boundaries. I need some calculation modulo some boundaries. Here this map goes Q tensor G1 tensor G2 goes to as always Q G1 G2 minus Q G1 G2 plus Q tensor G1, as always in bar resolution. And from this we obtain that we obtain the following thing. If Q is 1, for example, yes. And so I consider I consider this. But let me maybe consider this braces. This braces means that I consider homology classes in this place, modular boundaries. Okay. So modular boundaries, what this means that I have this equality. The thing equals to 0. What? If I consider this Q is unit, is a coset class of unit, then this is something like this. 1 tensor G is equal to 1 okay, 1 tensor H GH minus 1 tensor H, where G is from G and H is from H. No, this is true, yes, because if, for example, if G1, if Q is unit, G1, for example, is G, then I obtain G1 is H, yes, and Q is 1. So I obtain this is also 1, so 1 tensor G equal to plus minus 1 tensor GH plus 1 tensor H, or maybe HG. No, I want GH. Sorry. I want some more. Do you understand what's happening? Do you understand what's happening? Yes. I want, and using this boundary relation, I have this general relation. I have this relation. This relation that Q tensor yes, QG tensor H minus Q tensor GH plus Q tensor G equals to 0. What modulo this relation? I want to rewrite this thing. Yes. How I can do this? And I want to obtain from this relation that this is something like this. No, maybe G, where G is the representative of Q. It's what I want to check. That is action by adjunction. Okay, let me rewrite this thing as yes. If Q is unit, then it's unit. Unit, it's coset of H. This is coset of G. Okay. Yes, and then in the opposite direction, maybe yes, maybe it will be yes. Let me. I have G. It's H. H G H. If H is from H, then it's also unit. So I have something like this. Oh yes, it's my relation. No, and now it's true for any H from H and G from G.
So what?
А?
How?
Надо было следить. Но я к тому, что, ну, это просто вот то соотношение, где я взял, it's when I consider Q is unit, it's a coset of H. G1 is from H, it's H, and G2 is G. And if I multiply 1 to H, it's also 1, because it's the same coset. Yes. No, and now if I apply this identity to the what? No, yes, if I consider H, it's because H is normal subgroup, I can consider in place of H conjugation GH G minus 1. If I obtain here GH G minus 1, then this will be GH. And this will be G. No, this is, I think, what I want. Because yes, because here, what QH is a class of some element G, tensor H is equal to, oh no, yes, maybe I need the previous one also, equality, which I cleared up. It's always true that G tensor H equal to, as I said before, tensor GH minus tensor G. It's always true. It's by resolution. So this thing is equal to this difference. And this difference is equal to this thing. Yes, exactly. So I consider this by bar equality, no, by bar relation in general, and this is from also the particular case of bar equality. This is equality. So yes, in my first homologies, I have that this class is this class. So in my identification, I have that Q action on abilization is by a junction. Okay, let's do the break.